Hey guys, here's a little bit of extra help on assigning oxidation numbers and compounds. And this should be really, hopefully, pretty easy for you ladies and gentlemen, because believe it or not, you have already done this. Okay, if you think back to our chapter when we dealt with chemical nomenclature and when we had metals that came out of that central part of the periodic table, the ones that could take on multiple oxidation states. And we had to find the charge on them so that we knew what Roman numerals to assign in the name. That's exactly the same work we're going to be doing here. Exactly the same thing. So if we dig back in our memory, we were using a formula back then that said we're going to take the number of atoms present in a compound and we're going to multiply that by the charge. Actually, this should be oxidation number, but it's easier and shorter to write charge. And we don't really need to get into the formal differences between them, so I'm going to use a little shorthand. Anyway, we have the number of atoms of one element times the charge on each atom. And we're going to do that for every atom in our compound. And if we do that for every atom in our compound, those things have to add up to be the charge on the compound. Okay, so let's take a look at a couple examples and see this kind of at work. Okay, the first one we're going to do, let's do some thing that looks very familiar to us, or should, from our nomenclature chapter, because this is a multiple oxidation state metal, and if we were going to name this, well, we would have to find the charge on the manganese. That's exactly what we're going to be doing right here. Okay, so what I'm going to do, I'm going to start with kind of my knowledge on some of the rules to identify the oxidation states of something in this compound. I have to start somewhere. And almost always, hydrogen and oxygen are the places that you want to start if they're present in the compound. Because oxygen, unless it's in a compound with fluorine or it's in a peroxide, is going to have a charge of -2. And the good news is I'm not going to give you any peroxides in this class. I'd have to teach you to memorize them and or have you memorize them, and I'm not interested in doing that. And I'm pretty unlikely to give you an oxygenated fluoride compound. So we're really, for practical purposes in our class, you can say oxygen will always be a -2. So if we want to say what the oxidation number is on the oxygen in this compound, it's going to be a -2. And now we're going to go ahead and apply our formula now that we've kind of identified at least some information that we can put in here. So let's start with our oxygen. We have two atoms. Each of them have a -2 charge. We have one manganese atom with a charge that we don't know, or an oxidation number that we don't know. That's what we're going to be solving for. And they're going to add up to be the charge on this compound. Since there's no charge shown here, that's a 0. We end up with a very simple x minus 4 equals 0, or x equals +4 answer. That is the charge, now the oxidation number on the manganese in this compound. If we were going to name it, it'd now be in manganese 4 oxide, with that 4 representing that oxidation number. Okay. So let's see another example. Let's take a look at, maybe we'll do another nice easy one with hydrogen involved. Let's take a look at methane, carbon tetrahydride, and we're going to kind of do the same sort of approach, except now we're going to look at our hydrogen. And hydrogen only has one electron, and it can only accept 2 electrons in its valence shell. So hydrogen can either be a +1 or a -1. That's it. Can't be anything else. And it's really easy to determine which of those two, kind of, if it's a plus or a -1, because it's going to depend on its partner atom. If this partner is a nonmetal, then hydrogen will be a +1. If this partner atom is a metal, then hydrogen will be the negative one. Okay? Again, that just has to go with the electronegativity. Carbon's more electronegative than hydrogen, so carbon's going to take those electrons. Hydrogen's going to lose them, and hydrogen go positive charge. With a metal, hydrogen would be more electronegative, so hydrogen would take the electrons and get that negative charge. Anyway, in this case, since we're with a nonmetal, hydrogen's going to be a +1. We have 4 hydrogens. Each of them have a +1 charge. We have 1 carbon with an unknown charge, and those things have to add up to be the charge on the compound, which is, in this case, again, 0. And here we end up with a very similar answer, except in this case, our answer is a -4. So the oxidation number on the compound would be, on the carbon in the compound, would be a -4. Okay, now let's take a look at an example of something that isn't neutral. So let's take a look at the sulfite ion, and let's say, well, what's the oxidation number of everything in this particular compound? Okay. Again, we're going to start with oxygen. We're usually going to start with oxygen or hydrogen because those are the things we know the most about. There's a couple other things we know quite a bit about that we'll get to in a future example. But for here, we have 3 oxygens. Again, we know oxygen's not with fluorine. It's not in a peroxide, so it's a -2. I've got 1 sulfur. It's got an unknown charge, or oxidation number. I keep saying charge, and I should technically be saying oxidation number, so I apologize. The two are practically the same thing, but an oxidation number can exist inside of a covalent compound, whereas a charge can't. So when I say charge, I mean oxidation number, and I apologize for not being precise with my language. I will try to correct that for the remainder of this video. Okay. Anyway, sorry for that little aside. We had 3 oxygens, each have a charge of -2. We have 1 sulfur. We don't know its charge, but we know that the charge on the entire compound is -2. So just a little bit of math. Is simplifying our expression there, and then I'm just going to add the 6 to each side, and I'll find out that in this particular compound the sulfur would have a +4 oxidation number. Okay, so now let's take a look at an example of something. Actually, just go to a new page. Of something that contains neither hydrogen or oxygen. So let's look at a very simple example, but one that doesn't, that uses some of our other rules. So let's take a look at some potassium sulfide, K2S. Very simple equation here. And I don't see any oxygen, I don't see any hydrogen, so I don't have that easy starting point. But I have another pretty easy starting point, and that is the fact that the elements in group 1 and 2 have known charges. And by group 1 and group 2, I'm talking about those named groups on the periodic table, the alkali metals and the alkaline earth metals. And so if we have one of those present in the compound, we always know its charge. They will always be a +1 or a +2, depending on what group they come out of. In this case, potassium is an alkali metal. It's in group 1, so it gets a +1 charge. Therefore, I know the charges on everything except for one element in this compound, and I can solve for them. So I'm going to go ahead and I'm going to say, well, I have 2 potassium atoms. I know now that they have that +1 charge. I have 1 sulfur atom with an unknown charge, and those things must add up to be the charge on the compound, which is 0. In this case, again, I end up with x plus 2 equals 0, and so the charge on the sulfur should be -2. And now there's another way that I could solve this problem without even using any math in this particular case, because I can go to one of our other rules, which says that the more electronegative element gets the charge it would have in an ionic compound. Or I'm going to just shorthand this as gets the charge it wants. And remember, for electronegativity, generally speaking, you can look at the periodic table, and the closer that something is to fluorine, the more electronegative it's going to be. And in this case, sulfur is really close to fluorine. Potassium's really far away from chlorine. And so sulfur is going to get the charge it wants. It's more electronegative. And so in this particular case, I could just have used my knowledge that, hey, those elements in the same group as oxygen like to take on the -2 charge. Since this is more electronegative, it's going to get the charge it wants, so it's going to get a -2 charge. Either way works. The mathematical way will work every time, but so will kind of the judge of electronegativity for anything with a known charge. So that's another little rule trick to keep in your pocket. This one works. Mainly you want to use this. This will be your default rule if there's no HO or metal from group 1 or 2. Or aluminum. Aluminum has that known +3 charge. The same thing that, all those things that we talked about when we were in chemical nomenclature with the Roman numerals, those still apply here. Like cadmium will always be a +2, zinc will always be a +2, silver will always be a +1. Those things that could only take on a single oxidation state, they can, well, I'm going to retract that statement. That's incorrect. It can take on other oxidation states. So we shouldn't depend on that. They do so rarely and usually only judged or when combined into kind of polyatomic ions, but they can. Boy, I'm saying all sorts of things wrong on this video, I guess. Sorry. All right, let's do, get beyond that, and let's do an example of something maybe a little bit more complicated. And this one is going to take a little bit of extra thought in order to be able to, let's do this one, in order to tell the oxidation states of everything in here. So what if we start putting more than 2 elements together? And let's say we have, for example, and let's do that. Okay, so I've got a little iron 3 sulfate, and I want to find out what are the oxidation numbers of everything in this. Okay, so I'm going to start going through rules. Because if I look at my master equation, it's that number of atoms times the charge on each. Number of atoms times the charge on each has to add up to the charge on the entire compound. And so I can say, well, this thing's neutral, so all those things have to add up to be 0. But I'm going to run into a little bit of a problem here, because I'm going to say, well, I have 2 irons. Irons are not in group 1 or group 2. They're not aluminum. They don't have this known oxidation state. So we're going to just have to say, well, we don't know what the oxidation state is on the iron. We don't have a rule that applies to it. In this case, we have 3 sulfur atoms. 3 of these groups. So we have 3 sulfur atoms. And Sulfur, the only rule that can really help us with a nonmetal that's not oxygen or hydrogen, is that the more electronegative element gets the charge it wants. Well, oxygen is more electronegative than sulfur. It's closer to fluorine. So sulfur doesn't get the charge it wants, and we don't know what charge sulfur will get. So we're going to call that a Y. And we have 4 oxygen atoms, and of course, oxygen gets its -2 that it wants to have. And now I'm kind of stuck because I have 2 variables, and I can't solve 2 variables with a single equation. So I've got to use some other bit of knowledge to kind of find another equation that'll allow me to solve this. And what I'm going to do is I'm going to say, hey, wait a minute. I recognize that stuff. I know what that is. That's a sulfate ion. And so if I peel that out and look at what a sulfate ion is, it's going to be an SO4 with a 2- charge. Now I can look at just this piece, and I can find the charge on the sulfur out of it. Because for this piece, now I only have 2 elements, and I know one of their charges. So I'm going to say I have 1 sulfur. It doesn't have a known charge. And now I only have, oops, I'm so sorry. Boy, I'm making lots of mistakes. There were 12 oxygens up here, 3 times 4. Down here, there are only 4 oxygens because I'm only going to look at one of these polyatomic ions. And it's got a -2 charge. Those now have to add up to the charge on the compound, which in this case is 2-. So I've got a x minus 8 equals 2- or -2. And I've got that the charge on the sulfur is a +6. Now I can take and I can drop that back into my original equation, and I can say, well, 2 times something plus 3 times 6 plus 12 times -2 has to equal 0. I've got here -24, here's 18, so that's 2x minus 6 equals 0. And I can find out that my charge on my iron is a +3. Like that definitely works. That's kind of the formal way to do this. One of the other ways we can do this that'll be maybe a little bit more simple is we can kind of just replace this whole, while we're working on the stuff outside of the polyatomic, we can replace that whole polyatomic. And then that'll kind of allow us to make things mathematically a little more simpler. A little more simpler, huh? Yeah. Good English there, grammar man. Okay, so starting back with this Fe to SO43 thing. If I'm looking for the iron, what I can do is I can say, hey, I know that the charge on SO4 is a -2. So instead of in my equation putting in an atom for each, I'm going to put this in as a polyatomic ion. I'm going to say I have 3 SO4s. Each have a -2 charge. I have 2 irons with an unknown charge, and now they must add up to be 0. And so you can see here that we can get that charge on the iron really easily, as long as we just kind of look at the charge of the overall polyatomic. And then to find the charge on the sulfur, we would want to just peel that polyatomic apart like we did here, look at just the polyatomic ion, and run the same equation for that. So that should cover examples, I think, of all of the primary types of oxidation numbers that you would be asked to assign or would be assigned to complete. So if you have any further questions, please contact me via email or chat, and I will do my best to assist you.